Okay, good afternoon, everybody. My name is Ross Miller, and I'm a software developer for Oak Ridge National Laboratory, and I'm here to talk about some of our first impressions with the Fujitsu A64FX processors that we recently installed in our Wombat cluster here at ORNL. So, to start with, Wombat is a small research cluster based on the AR64 architecture. It started out as a part of HPE's Project Comanche that eventually led to the Apollo 70 product line. It's based on Marvell ThunderX2 processors. Currently, we have 8 ThunderX2 nodes. Each node is a dual socket, 64 cores total. 256 gigabytes of RAM, EDR InfiniBand, and onboard SATA SSDs for node local storage. Shortly before SC'19, we went and upgraded these nodes, 4 of these nodes, with NVIDIA Volta GPUs. We put 2 GPUs per node into 4 of these nodes. And that was basically a mad scramble to get those up and running and have CUDA installed in time for people to actually try it out and have some numbers to report at SC last year. Additionally, besides the compute nodes, we do have 2 login nodes that are based on ThunderX2s, and also our management servers are actually x86-64. Now, most recently, in what seems to be something of a tradition, right before SC, we went and upgraded the hardware again. This time around, we added 16 nodes of Apollo 80. These nodes each have a single A64FX processor in them. And what is very interesting, as everybody all excited, of course, is that these processors do in fact implement the SVE instruction set. There's 48 cores per processor, and additionally, there's 32 gigabytes of HBM2 memory on the CPU package. According to Fujitsu, this processor is capable of a terabyte per second of main memory bandwidth and 2.7 teraflops double precision floating point. Besides the processors, the nodes also have EDR InfiniBand and onboard NVMe devices. And in particular, we actually configured some of the NVMe as swap space to compensate for the limited amount of system memory. And I will talk about that shortly. As far as administering the cluster goes, there's a couple of challenges here. Some of them are obvious and some of them a little less so. On the more obvious side of things, this is a heterogeneous node architecture. We've basically got 3 different types of compute nodes, the ThunderX2s by themselves, ThunderX2 plus GPU, and now the A64FX nodes. Furthermore, the A64FX nodes really have a very small amount of system memory on them. That 32 gigs of HBM is all that there is. These nodes don't have any additional DDR memory anywhere. On the somewhat less obvious side of things, we also had a rather limited amount of administrator resources. Right now, it's just me and one other fella helping me out, and neither of us are full-time on this. We both have other duties to attend to. Furthermore, we were under some pretty significant time pressure to try and get these A64FX nodes online in time for SC'20 this year. Because of that, we had to make some decisions that prioritized ease of administration over absolute performance. So, among other things, despite the fact that it's very different types of compute nodes, we did end up deciding to use a single boot image for all of the compute nodes and the login nodes. And that means that this image has the CUDA libraries installed, it has the compilers installed. And that just makes it rather big and bulky. Furthermore, these node images are loaded into tempfs partitions, i.e. RAM disks. And that further significantly cuts into the amount of memory available on the A64FX nodes. Now, as I alluded to before, we are able to mitigate that somewhat by using swap space. The tempfs file systems really are designed to actually be swapped out, and that works quite well. Since the tempfs images, the boot images, are mostly read-only, once things do get swapped out, they don't have to be ever written to disk a second time. If they get brought back in for some reason into main memory, swapping them out again does not really cost any time. So this whole idea of swap in an HPC environment, I thought was something I should really bring up and talk about. You almost never hear about swap on HPC resources, and for good reason. However, the Apollo 80 architecture is kind of atypical, and as was our choice to prioritize convenience over performance. In our case, swap seemed to be a fairly elegant and inexpensive solution. It basically allows all 32 gigs of RAM, minus the kernel, to be available to users' codes when the codes are running. The boot images, although they're needed for certain things, they don't actually need to be in RAM all the time. Now, even though we do have swap, you still have to be careful about your problem size and making sure your problem will fit in memory. In the standard clusters where there isn't swap, if your problem exceeds the problem size of the RAM, if your problem size exceeds the available memory on the node, your program crashes, and it's pretty obvious what happened. When you've got swap enabled like we do, if your problem size exceeds the memory available memory of the node, your program just runs slowly. It doesn't crash, and now it's not really clear why your program is running so slowly. So that is something that we do have to be careful with now. But having said that, I've been thinking about this now a little bit, and I'm beginning to wonder if maybe swap will start to make a comeback in HPC environments. Now, clearly, our use case on Wombat is something of a niche use case. But if we start seeing more cases where the memory is directly on the CPU package and can't be upgraded, and in particular, if the memory to core ratio continues to decrease like it has with the Apollo 80s, where there's less than 1 gig of RAM per core now, I'm wondering if swap might start showing back up, in more use cases. Anyway, it's something to think about, and something I'm kind of interested to see what happens in the future. Okay, on to some very preliminary performance numbers. So just as a reminder, these new A64FX nodes have only been online for about a month at the time of me making this recording, so we haven't had a lot of time to really optimize anything. I did try to make some initial runs with HPL and HPCG. I am not well versed in the arcane art of tuning these benchmarks, and the results show it. Specifically, I was able to get maybe 20 to 25% of the performance that I probably should be able to get. That is, I ran some single node tests and compared that with what was reported on the top 500 list by the Fugaku engineers. And like I said, 20 to 25% of what the hardware should be capable of. I am 99% certain that that is more a case of just tuning the benchmark runs rather than any sort of problem with the problem with our hardware or anything like that. On more happier news, we were able to run the Stream Triad benchmark and get some pretty good results there. Big thanks to Eric Nielsen at NASA and Mohammed Zubair at Old Dominion University for running this benchmark. What seems to be interesting about this, or at least that I find interesting, is that the benchmark does still seem to be highly compiler dependent. the 816 gigabyte per second number was achieved using a build of GCC from the master Git repo, the master branch of the Git repo. When we tried to build it with GCC 10.2, which is the latest that's actually been released, they only achieved 622 gigabytes per second. And finally, I don't know what order these videos are going to be presented in, but pay close attention to what John Stone is going to be presenting about NAMD and VMD. He has some very interesting things to say about porting those codes over to SVE and what his experiences were on Wombat. So assuming it hasn't been presented yet, that will be a very good presentation to watch. Conclusions and closing remarks. When we first thought about getting these nodes, my first thought was, I very much wanted to try out the SVE instruction set. However, after having these nodes for a little while and doing some experimentation with them, it seems like actually the memory bandwidth from the HBM may be the most useful thing, not the SVE. In any case, they're both very interesting architecture choices that I'm going to be very interested in seeing how applications can take advantage of those in the future. The second point I wanted to make is it does seem to be that the compilers are still improving in their support for SVE. Like I said, with the stream benchmark, we had to run an unreleased version of GCC to get the highest performance. On a related note, I've heard some very interesting things about Fujitsu's compiler for the A64FX, and I'd really like to try it out. So if anybody from Fujitsu is listening in to this presentation, please contact me. We're really very interested in getting a license to run that compiler. And finally, one final note is that Wombat is in fact an open system. If you're at all interested in trying out your favorite codes on the AH64 platform, please do apply for an account. Just take a look at the web page listed at the bottom of the screen here and apply. It's actually very simple to get on, and we're happy to let others use the system. So thank you very much for listening, and I hope everybody has a good day.